In the second part of today's lecture, we're going to focus on chemical equilibrium. So up until this point, we've really thought of reactions as occurring completely from reactants to products, but in reality, many chemical reactions are reversible, and in many cases, a mixture of reactants and products are present, and a chemical equilibrium is established that's dynamic. So we want to be able to discuss chemical equilibrium quantitatively, and so in order to do this, we need to understand the concept of the equilibrium constant K and how it can be used to determine whether a reaction is reactant or product favored. And then we'll also look at the reaction quotient Q, which basically tells us if we have a mixture of reactants and products, whether the mixture is at equilibrium, and if it's not, whether or not the forward or reverse reaction has to occur to establish equilibrium. So we'll first look at kind of a qualitative example, and our goal is to eventually be able to explain the observations that we make about this. So if we dissolve cobalt 2 chloride in water, what is actually present in solution is what we call a hydrated cobalt 2 complex. So this complex has basically a series of ion dipole interactions between the cobalt 2 plus ion and water. So electron density is shared between the water and the cobalt 2 plus, and we'll look a little bit more closely at this type of interaction later on in the semester. So the cobalt aqua complex is red. If we add an additional source of chloride ions, some of this red cobalt aqua complex converts to a cobalt chloride complex, which is blue. And at a certain point, equilibrium is established where there's a mixture of the red cobalt aqua complex and the blue cobalt chloride complex. And the way we can tell that there must be a mixture of the two is that the solution is actually purple. So the purple solution indicates that we have some mixture of the red and the blue complexes, giving us purple color overall. So there are various changes that we can make to the system that disturb the equilibrium and causes the concentrations of reactants and products to change. And we saw this a little bit when we discussed solubility and the effect of temperature, and we'll come back to this later in the chapter. But basically, if we make a series of adjustments to the solution, we see a visible change occur. So if we cool the solution, the color becomes more red, and that indicates that the more of the aqua complex is present. If we heat the solution goes blue, indicating that we have more of the cobalt chloride. So when we add heat to the solution, the forward reaction occurs, and so this indicates that the forward reaction is endothermic, just like we saw for solubility of ionic compounds. So we add heat, and the forward reaction occurs, so heat must be a reactant. If we cool the solution, the opposite occurs, so the reverse reaction must be exothermic. Now, if we add HCl, we see that the solution becomes more blue again, and so this indicates that more of the cobalt chloride has formed, and so the forward reaction occurred to a larger extent. If we add water, we see that the solution becomes more red, indicating that more of the aqua complex formed. So we can explain this in terms of equilibrium and Le Chatelier's principle, which we saw briefly, and we'll come back to making these explanations once we've kind of looked a little bit more in depth at chemical equilibrium in general. So we've looked at chemical kinetics, and we're now going to look at equilibrium, and it's important to differentiate between the two. So we've seen that chemical kinetics applies to the rate of chemical reaction, and so using integrated rate laws, for example, we can examine the change in concentration of product over a certain period of time, or the change in concentration of reactants. So kinetics has to do with how fast the rate occurs, and we saw that that's going to depend on the activation energy for the reaction. Equilibrium refers to basically the extent of reaction, so how much products are actually being formed, or the concentration of product that would appear if you gave the limited amount of time to react. So it's important to differentiate between kinetics and equilibrium. Kinetics has to do how fast something will form, equilibrium has to do with how much of something will form. And so we'll look at a few examples of this. So if we first look at dissociation of acids in water, we know that HCl is considered a strong acid, so it's a strong electrolyte, and so we say that it dissociates completely in water. And so we normally talk about it being a case where we don't have any molecular HCl remaining, we just have hydronium ion and chloride ions. Now, acetic acid, the next one down, is a weak acid. So in this case, most of the solution consists of molecular acetic acid with a small amount of hydronium and acetate ions. So the dissociation of hydrochloric acid in water is a fast reaction, and we say that it has a large extent. So when equilibrium is established, the concentrations of hydronium and chloride are very high, and the concentration of HCl is very low. So this is a fast reaction that occurs to a large extent. So very quickly, we can form large amounts of hydronium and chloride. The dissociation of acetic acid, on the other hand, is also a fast reaction, so it's going to form hydronium ion quite quickly, but it occurs to a very small extent. So when equilibrium is established, there's very little hydronium and acetate present. The vast majority of the components of the solution are the acetic acid. So we can have fast reactions that occur to either a large or a small extent. As another example, we can look at reactions that occur in a steel storage tank. So this first reaction is the reaction of iron with molecular oxygen and water to form iron oxide, and this is just the formation of rust. So we know that formation of rust on steel takes a fairly long amount of time to occur, but if given a sufficient amount of time, a large amount of rust will form on iron-containing components. So this is a slow reaction. The kinetics of the reaction are slow, but it occurs to a large extent. So given an infinite amount of time, a large amount of the iron oxide can form. Another reaction that could potentially occur in the storage tank is the decomposition of water to form oxygen and molecular hydrogen. Now this is a reaction that is also very slow, but it also occurs to a very small extent. So over a period of time, iron will rust in the steel tank, but very little water is going to be converted to oxygen and hydrogen. So it occurs very slowly, and very little of the conversion actually occurs once equilibrium is established. So when we think about reactions, we want to think about both whether or not any product will form in a reasonable amount of time, and how much product will form in a reasonable amount of time. So a reaction that would be working well from a synthetic standpoint, for example, is something that occurs at a high rate and has a large extent. So for any reaction, we can define what's called an equilibrium constant. So we know that when an equilibrium is established, it's a dynamic equilibrium. So if it's a chemical reaction, reactants are being converted to products and products are being converted back to reactants. And equilibrium is established when these two rates become equal. So when the rate of the forward reaction is equal to the rate of the reverse reaction. So if we have a simple reaction where we just have A converting to B, that means that the rate of the forward reaction would be the rate constant times the concentration of A, and the rate for the reverse reaction would be the reverse rate constant times the concentration of B. So this can be rewritten as the concentration of B over the concentration of A, which is equal to the ratio of the rate constants, and this is defined as the equilibrium constant, which is a capital K. So just kind of a note to be aware of when you're doing these problems is to not confuse the fact that the rate constant is a lowercase k and the equilibrium constant is an uppercase K, and in both cases these are depicted in italics. If we see a non-italicized capital A, that indicates Kelvin temperature. So it's just good to be aware of the three different Ks and knowing what the differences are. So if we have a more complicated reaction where we have A and B going to C and D at some temperature, the equilibrium constant Kc, and the C just indicates that it's in terms of concentration. the equilibrium constant Kc will be equal to the concentrations of the products raised to the power of their stoichiometric coefficients, divided by the concentrations of reactants raised to their stoichiometric coefficients. So this is referred to as the equilibrium expression. So it expresses the concentrations of products and reactants to give us the equilibrium constant. So if we look at a few examples of this, of writing the equilibrium constant, for the equilibrium between dinitrogen tetroxide and nitrogen dioxide, we can write the equilibrium constant Kc as being equal to the concentration of nitrogen dioxide squared, because the stoichiometric coefficient is 2, divided by the concentration of dinitrogen tetroxide. And in that case, it would be raised to a power of 1, and usually the 1 is excluded from the equilibrium expression. Now, when we have a more complicated reaction, like the reaction of ammonia with oxygen, we're going to look at the products of the concentrations. So we'd have the concentration of nitrogen monoxide raised to the 4th times the concentration of water raised to the 6th, divided by the concentration of ammonia raised to the 4th times the concentration of O2 raised to the 5th. So the equilibrium constant expression will always include concentrations of products raised to the power of their stoichiometric coefficients divided by the concentrations of reactants raised to their coefficients. So we can calculate K for a given reaction. So for the reaction of hydrogen with iodine to form HI, Kc is going to be equal to the concentration of HI squared divided by the concentration of H2 times the concentration of I2. And so if we know either initial concentrations or concentrations at equilibrium, we can use them and the expression for the equilibrium constant to calculate an equilibrium constant. So if we have a flask at 425 degrees C that contains hydrogen and iodine in equal concentrations, over time equilibrium will be established, and our final concentration of H2 is 0.0037 and the concentration of HI is 0.0276. So from this information we can calculate the equilibrium constant K. So if we were to first just think about the change in concentrations of reactants and products over time, we would see that because we started out with equal amounts of hydrogen and iodine, their concentrations are going to decrease at equal rates because they react in a 1-to-1 ratio. And the concentration of HI is going to increase at twice the rate because for every 1 molecule of H2 and I2 that react, we form 2 molecules of HI. So we can use all of this to calculate the equilibrium constant K. And for many equilibrium calculations, we use what's called an ICE table. So in an ICE table, we write our chemical reaction, and we write concentrations at 3 different points in time. I is for initial, C is for change, and E is for equilibrium. So in the ICE table, we're always writing concentrations of reactants and products. And so we want to start by writing in the values that we know. So we're told that initially we have 0.0175 molar of both H2 and I2. And because we're just starting with reactants, that means that our initial concentration of HI is going to be 0. And then we know something about our final conditions. So we know that at equilibrium, we have 0.0037 molar of H2, and we have 0.0276 molar of HI. So now basically we have enough information that we can determine all of the equilibrium concentrations. So we know that the change in HI must be plus 0.0276 because we didn't start with any HI initially. And then we know that the decrease in H2 must be minus 0.0138, which actually is half of the increase in HI, which makes sense because for every 1 molecule of H2 that reacts, we form 2 molecules of HI. And because H2 and HI were present in equal concentrations to begin with, that means that the final concentration of I2 is going to be the same as the final concentration of H2. And so the change in I2 is the same. So now we can use our equilibrium constant expression, concentration of HI squared, and we can input the values that we just determined or were given. And so if we multiply that out, we get a value of 56 for our equilibrium constant. So there are a set of rules for writing equilibrium expressions, in addition to the fact that it's products over reactants all raised to their stoichiometric coefficients. So the first is that K doesn't have units. We have products in the numerator and reactants in the denominator, and each of them each concentration is raised to the stoichiometric coefficient. And all concentrations are equilibrium values, so we can only calculate K if we know that if the concentrations we're working with are equilibrium concentrations, so we know that the system is at equilibrium. And K is always going to depend both on a particular reaction and also on the temperature. So K for a particular reaction will vary depending on the temperature at which it's occurring. So in these expressions, we always include concentrations of gases and concentrations of solutions. We never include solids, pure liquids, or water, which counts as a pure liquid. And the reason for this is that in the equilibrium constant, we really want to be thinking about changes in concentrations. But because solids and pure liquids aren't actually part of the solution or the mixture, the homogeneous mixture, we can't talk about their concentrations changing because they're not actually applying to the concentration of reactants and products. So if we look at a couple more examples of equilibrium constant expressions, we see that if we have solid sulfur reacting with oxygen, we form sulfur dioxide. And so K for this reaction would be the concentration of sulfur dioxide divided by the concentration of oxygen. So in this case, because it's a solid, sulfur is excluded. So that doesn't mean that the sulfur isn't being consumed in the reaction. It's just not contributing to the equilibrium constant. So as another example, if we come back to the dissociation of HCl, this equilibrium constant would be the hydronium ion concentration times the chloride ion concentration divided by the concentration of HCl. So in this case, we exclude water from from the equilibrium constant because it's a liquid. So now that we've looked at the equilibrium constant, we want to talk about what it actually means. So if we have a general reaction where we have A and B going to C and D, we've seen that we can write the equilibrium constant expressed in terms of concentrations of reactants and products, but often reactions occur in the gas phase, and so we can actually also define the equilibrium constant in terms of partial pressures. So Kc refers to the equilibrium constant in terms of concentrations. Kp refers to the equilibrium constant in terms of partial pressures of reactants and products. And so it turns out that if you know the value for either Kc or Kp, you can calculate the other one by this relationship. So this relationship can be derived from the ideal gas law. So if we have a reaction where we just have A converting to B, we know that we can relate pressure, volume, temperature, and number of moles by the ideal gas equation. And we can rearrange this to express pressure in terms of number of moles, temperature, and volume. And this term, N over V, is the molarity. So we can express pressure in terms of molarity and temperature. So now if we write the equilibrium constant in terms of pressure, Kp is going to be equal to the partial pressure of B raised to its coefficient divided by the partial pressure of A raised to its coefficient. And because of the relationship that we just wrote, we know that the partial pressure of B is going to be equal to the concentration of B. And so we can rewrite this as concentration of B times RT, all raised to the power of B. And then the concentration of A times RT raised to the power of A. And we can factor out the RT term, and so we can write this as concentration of B raised to the B divided by concentration of A raised to the A times RT raised to A minus B, or B minus A. So this whole term is Kc, and B minus A is going to be the change in the number of moles of gas, or delta N. And so that can be rewritten as Kc times RT raised to the delta N, which is the term that we had shown here. So we want to understand what the magnitude of K actually tells us. So we now see how it can be calculated based on initial and final concentrations, but we want to actually understand what it means. So if we look at the reaction of nitrogen monoxide with ozone, it forms nitrogen dioxide and oxygen. And an expression for Kc can be written. Everything is in the gas phase, so we can write concentrations or pressure or partial pressures of reactants and products. And if this was measured experimentally, it was found that at 25 degrees, the equilibrium constant is 6 times 10 to the 34. So in this case, the equilibrium constant is a very large number. And if we think about the components of the equilibrium constant, we can kind of predict what it means. So in the equilibrium constant, we have concentrations of products being divided by concentrations of reactants. So if when we take that ratio we get a very large number, that must mean that at equilibrium we have much higher concentrations of products because they're in the numerator than we do reactants in the denominator. And then kind of on the opposite end, if we look at the reaction of oxygen to form ozone, we see that the equilibrium constant would be concentration of ozone divided by concentration of oxygen raised to the 3/2. And if this is measured at 25 degrees, we have a very small value for the equilibrium constant. So now the equilibrium constant is 2.5 times 10 to the minus 29. So what this tells us is that the concentration of ozone must be much smaller than the concentration of oxygen raised to the 3/2. So if we have a value for the equilibrium constant that is much greater than 1, that means that the concentrations of products are much greater than the concentrations of reactants. And so we say that this is a product-favored reaction, and we say that the equilibrium lies to the right. The equilibrium lies to the product side. And we also can say that this means that the reaction occurs to a large extent. We have a large conversion of reactants to products. Conversely, if we have a K value or an equilibrium constant value that's much less than 1, in this case the reverse is true. We have a much lower concentration of products than we do reactants. And so we say that this equilibrium is reactant favored and the equilibrium lies to the left. So it's more of the components on the left side of the equation that are present. And so we say that this reaction occurs to a small extent. Now, in the case where we have an equilibrium constant close to 1, this tells us that we have nearly equal concentrations of reactants and products. And so one reaction isn't significantly favored over the other one. So as I mentioned before, the value of K is calculated by equilibrium concentrations of reactants and products. But when we initially mix reactants and products, we're not necessarily at equilibrium. And so in order to discuss reactions that haven't reached equilibrium yet, we define what's called the reaction quotient Q. So the expression for the reaction quotient is the same as the equilibrium constant expression. So you calculate Q by taking the concentrations of products raised to their stoichiometric coefficients and dividing by the concentrations of reactants raised to their stoichiometric coefficients. The difference is that the concentrations that you use are not equilibrium concentrations. So the reaction quotient can be calculated when we are not at equilibrium, when we just have a mixture and we want to know how the reactant and product concentrations will change in order to establish equilibrium. So if Q is equal to K, then that means that the system is at equilibrium. If Q doesn't equal K, then that means that it's not at equilibrium, and we want to know how the concentrations will change in order to reach equilibrium. So again, we can compare Q and K to predict the reaction direction. So Q again takes on the same form as K, we're just calculating using non-equilibrium concentrations. So if we have a situation where Q is greater than K, basically that indicates to us that we have more products present than reactants than we would at equilibrium. And so in order to reach equilibrium, basically we need to get rid of some of those products by converting them to reactants. So when Q is greater than K, we increase the concentration of reactants and decrease the concentration of products via the reverse reaction. When Q is equal to K, the system is already at equilibrium, and so no shift is going to occur. The concentrations of product and reactions will remain constant. Now, if you recall, equilibrium is dynamic, and so the forward and reverse reactions are still occurring, but there's no net change in reactant or product concentrations. And then if Q is less than K, basically you can think of the denominator in the Q expression as being too large, And so in order to reach equilibrium, some of the reactants have to be converted to products. And so in this case, we'd see an increase in the product concentration and a decrease in the reactant concentration.